sequence impedances and networks of a synchronous generator. So in the previous class we have discussed about the sequence impedances of a symmetrical circuit, and we have proved that the currents of any given sequence produces voltage drops of the same sequence only. That means a positive sequence current will produce a positive sequence voltage drop. Negative sequence current will produce a negative sequence voltage drop. So we have seen that the sequence impedances are uncoupled in the case of a symmetrical circuit. So if you look on to the three-phase synchronous generator, we can draw three separate sequence networks: positive sequence network, negative sequence network, and zero sequence network. So let us consider a three-phase equivalent circuit of a generator as shown in this diagram. So the three phases are A, B and C. The EMF induced in the three phases are EA, EB and EC respectively. The currents in the three phases are IA, IB, IC respectively. And we have the neutral wire grounded through a neutral impedance ZN. So the neutral current IN flows through the neutral wire. Okay. So in the case of a balanced circuit, we know IA plus IB plus IC will be equal to 0. So no current flows through the neutral wire in the case of a balanced circuit. So IN will be equal to IA plus IB plus IC, which will be equal to 0. Okay. Whereas in the case of an unbalanced circuit or an unbalanced load, there will be some neutral current. Okay. So if you look on to this diagram, it is a three-phase generator. So it should supply balanced three-phase voltages. A three-phase generator should supply balanced three-phase voltages. Okay. So in the previous lectures, in problem number 6, we have already proved that a balanced set of three-phase voltages will have only positive sequence component. Okay. So we have seen that a balanced set of three-phase vectors will have only its positive sequence component. Okay. So that is in problem number 6. We have proved VA is equal to VA1. Okay. VA is equal to VA1. So here generated EMFs will be having positive sequence only. So why a balanced supply will have only positive sequence generated EMF? So what is the definition of a balanced three-phase supply? The three-phase voltages produced will be having the same magnitude, the positive phase sequence ABC, and the phase angle between the three phases will be 120 degree displaced from each other. So for a circuit to be a balanced circuit, these three conditions has to be satisfied. And we have already seen the definition of a positive sequence component. So what is the positive sequence component? It will have all the the positive sequence components will be having, that is VA1, VB1 and VC1 will be having same magnitudes, positive phase sequence ABC, and they will be displaced, that is VA1, VB1 and VC1 will be displaced from each other by 120 degree. So we can say that only the positive sequence components satisfies the criteria of a balanced system. Okay. So hence a generator which is designed to supply a balanced three-phase voltage will produce generated EMFs in positive sequences only. Okay. So let us consider Z1 as the positive sequence impedance, Z2 as the negative sequence impedance, and Zg0 as the zero sequence impedance per phase of the generator. So let Zn be the neutral impedance. So in the case of drawing the positive sequence network, we have to consider EMF in series with the positive sequence impedance. Okay, so the positive sequence network will have an EMF in series with the positive sequence impedance. Okay, and since it is a symmetrical net circuit, we can analyze it on per phase basis. Okay. So this circuit diagram shows the positive sequence current paths IA1, IB1, IC1. suffix 1 denotes that it is a positive sequence component of currents. Z1 positive sequence impedance, EA, EB, EC generated EMFs in the three phases. On per phase basis, the positive sequence network is drawn like this. An EMF in series with Z1. The current IA1 flows. Okay. So since the generator supplies the current direction is shown from the generator towards some external circuit. Okay. So we know current flows from higher potential to lower potential. So that is the reason why we have taken the polarity across this impedance Z1 as shown in the diagram. Because of this current direction, we have taken plus minus. Okay. So now by applying KVL to this loop, you will get VA1 is equal to EA minus IA1 Z1. VA1 is equal to EA minus IA1 Z1. Okay. So coming to the negative sequence network, we consider only the negative sequence impedance. We don't consider the generated EMFs. Why? What is the reason we removed the generated EMF? Because negative sequence components doesn't satisfy the characteristics of a balanced system. So it has same magnitude, even it will have 120 degree phase angle, but it is not having ABC sequence. Okay. So the negative sequence vectors or the negative sequence components cannot produce a balanced three-phase supply. Okay. So that is the reason why I have told in the first itself, generated EMFs can be positive sequence only. Okay. So that is the reason why we didn't show the EMFs in drawing the negative sequence network. We have taken only the negative impedance Z2. Because of this current direction, the polarity of Z2 is assigned as such. So what is VA2? VA2 is equal to minus IA2 Z2. VA2 is equal to minus IA2 into Z2. So coming to the zero sequence network, again there is no generated EMFs. ZG0, we take it as ZG0, IA0, IB0, IC0 are the zero sequence components of IA, IB, IC respectively. So coming to the zero sequence current path, we have to include the neutral current path also. Okay, so that is the reason why we have shown Zn here. Okay, so now when you draw the equivalent circuit or the zero sequence network, Zg0 is the zero sequence impedance of the winding, per phase winding of the generator. 3Zn is the neutral impedance. Okay, so synchronous generator is also a symmetrical circuit. So in the yesterday's class derivation, we have seen zero sequence impedance Z0 is equal to Z plus 3Zn, where Zn is the neutral impedance. Okay, so the same relation we have used here, Zg0 plus 3Zn. So the summation of Zg0 and 3Zn will give you the total zero sequence impedance component Z0. Okay, and IA0 is the zero sequence current drawn with respect to A phase. So when you apply KVL to this loop, what you will get? VA0 is equal to minus Z0 into IA0. VA0 is equal to minus Z0 into IA0, where Z0 is equal to Zg0 plus 3Zn. Okay. So now you should clearly understand why we have not used this neutral wire in the case of a positive sequence as well as a negative sequence network. Okay. So what are positive sequence components? IA1, IB1, IC1. They mutually differ by 120 degree. Okay. Even in the case of negative sequence components, IA2, IB2 and IC2, they differ mutually. These three negative sequence components will differ mutually from each other by 120 degrees. Okay. So when you add IA2 plus IB2 plus IC2, you will get 0. In the same way, when you add IA1 plus IB1 plus IC1, even that it will be equal to 0. So the current through the neutral wire will be nil. Okay, so that is the reason why we have not taken the neutral wire while drawing the positive and negative sequence network. Okay, so IA1, IB1, IC1 mutually differ by 120 degree. In the same way, IA2, IB2, IC2 also mutually differs from each other by 120 degree phase angle. So the summation of the three negative sequence components will be 0. Summation of three positive sequence components also will be equal to 0. So IN will be equal to 0. That is the reason why we have not taken ZN. Okay. And you know the reason why I have not included generated EMFs in negative and zero sequence network. Why we have not included? Because only a set of positive sequence components will be a balanced set. Okay. So the only a positive sequence component set can generate a balanced three-phase voltage. So that is the reason why we have taken only EA, EB, EC only in positive sequence network. Okay. And coming to the zero sequence, we know zero sequence components IA0, IB0, IC0 will have the same magnitude, but they don't have 120 degree phase relation. All the three will be in parallel. So IB0 will be equal to IA0, IC0 will be equal to IA0. So IN, that is the current through the neutral wire, will be equal to IA0 plus IB0 plus IC0. That is IA0 plus IA0 plus IA0, which is equal to 3 IA0. So since there is a neutral current, IN is equal to 3 IA0, we have represented the neutral impedance over here. Okay. So I will just read out the summary. Positive sequence network consists of an EMF in series with positive sequence impedance. Negative sequence network will not have any EMF. It will have only negative sequence impedance. Zero sequence network will not have any EMF source, but the total sequence impedances Z0 is equal to Zg0 plus Z3Zn. Positive and negative sequence currents are balanced current. Hence, there will not be no neutral current. Okay. So when the generator is delivering an unbalanced load, current flows through the neutral. Okay. The current through the neutral reactance is 3 IA0. So from the sequence networks, we can arrive at the following equations: VA1, VA2, VA0. So those are the sequence components of phase A voltages. Positive sequence component, negative sequence component, and zero sequence component of phase A voltages. Okay. So now, whatever we have discussed till now, we have considered the neutral grounded through a neutral impedance Zn. Suppose when the neutral is directly grounded without Zn, we remove Zn. Okay. And in the case of zero sequence network, when neutral is ungrounded, that is the current IA0 is equal to 0. That means it is left open. So these are the two special cases of zero sequence network.